Hello everyone. If we're not already on first name terms, I'm Sheila, sometimes aka Shirley Not, and sometimes MIDI-in. If you do know me, you may be expecting me to talk about something musical at this point, but for the next 10 minutes I'd like to talk about how I drive neopixels using a standard RC2014. I'll talk about what they are, how they work, why this shouldn't be possible, and what we can do to make it possible. Neopixel is an Adafruit trademark. We're actually talking about RGB, so-called addressable LEDs that follow the WS2812 standard. Note that there are some other compatible numbers and similar devices that aren't compatible. Even within the 2812, there are RGB, sometimes GRB, and there are some that are RGBW. The fourth white LED has some pros and cons, but we'll be sticking to the 3 LED WS2812. These LEDs come in various small packages containing a red, green and blue LED, plus a little chip that handles the serial protocol, remembers the colour and drives the LEDs. So as a programmer, you only have to send the colour and it'll remain lit at that colour and brightness until you tell it differently or remove the power. Each package has 4 connections, sometimes broken out to 6 pads, 2 for 5 volts, 2 for 0 volts, to make them easier to daisy chain. Besides power, they have a single line for data and another for data out. They have a very clever trick up their sleeve which allows you to daisy chain them with minimal wiring. 24 bits of data represent a colour, that's 8 bits per LED. Your first pixel will eat the first 24 bits of data that you send. When it's had its fill, it'll start to pass the data through, meaning that your second pixel only starts seeing data on your 25th bit, and it'll do the same, and so on. I believe they actually repeat the data rather than simply passing it through, which is good for keeping the data clean no matter how many you string together, and useful because you can use a dummy pixel as a repeater if you have long wires. This is why I personally think it's wrong to call them addressable. You can't just change the colour of any pixel you like. You've got to send the data for every pixel up to and including the one you want to change. So serial access rather than random access. Let's have a look at the serial protocol. As mentioned, it's a single line, so not clocked. And you'd think that that meant that timing is very important. But it isn't as critical as you'd think. Zeros and ones are both represented by a high pulse, the longer pulse being a 1 and the shorter pulse being a 0. In my diagram here, I'm showing a 0 bit and a 1 bit. In reality, you'd have 24 ones and zeros per pixel in rapid succession. Obviously, the specification puts actual numbers to the parts of the signal. In practice, it turns out that some of these parameters are critical, some are not. So what's important? Obviously, there's a threshold where a 0 bit has to be short enough to qualify as a 0 bit. And the gap in between your bits is important. It has to be short enough because a longer gap is taken to be an end of data or reset. And the next bit will be treated as the first bit by the first pixel. Other than that, there's a lot of flexibility with this. I believe you can hold the 1 bit high as long as you like and things will still work. Then obviously at the end of the data, the gap, which means end of data or reset, can be as long as you like. And again, without going into the actual numbers, this is the reason for Adafruit's claim that you need a processor running at least 8 MHz to drive these. If we run repeated I/O requests on our Z80 here, which is running at 7.3 MHz, to drive a line high and low and create this data signal, it's not fast enough to make those shorter timings. However, it's not too slow to trigger the start of each bit and then be ready to trigger the start of the next bit. Therefore, all we need is a pulse generator that generates a pulse that's the right width for a 1-bit or a 0-bit, triggered by our I/O request. We can do that with just a resistor and a capacitor and a logic gate. On my boards, I've made the resistor a trim pot so that we can fine-tune the width of the pulse. There's a cheat here, which is that if we decode the I/O request to our port, we happen to get a low pulse which is just the right width for a 0-bit. So all we need to do is invert that, and then we just need one of our pulse generators. Incidentally, I've demonstrated this working on a Spectrum using this same NeoPixel module and Colin Piggott's Spectrum to RC2014 module adapter. Obviously the Speccy is running at half the clock speed of our RC2014 here, meaning that our cheat now produces a 1-bit rather than a 0-bit. So all I had to do was retune the pulse generator to be a 0-bit and just reverse the bits in software. And that worked on a ZX Spectrum at 3.5 MHz. So moving on from the hardware to the software, I mentioned that making repeated out instructions allows us to trigger the start of each bit. So there's a further trick needed here because there's no room between those out instructions for reading our buffer, shifting the bits and conditionals. If it's a 1, do this. If it's a 0, do that. What we need to do is unroll those I/O requests and generate a subroutine in advance. I'm using one port with the in instruction triggering a 1-bit and an out instruction triggering a 0-bit. We set aside enough memory for the number of bits we want to send ahead of time. We just write those I/O requests into the right place in that memory. In fact, we can do that as we go. Every time we want to set the colour of a pixel, we calculate the position in that buffer and unroll 24 of these in and out instructions. Stick a C9 at the end for return from subroutine, and when we're ready to actually update the display, just call it. With that core library code written, all we need for easy programming is an API. Some simple functions for setting a colour by pixel number, by row and column, and then we just need to provide what I'm calling a show function, which actually sends the data to the pixels as just described. So this is our API. I'm sorry for mixing up assembly and C in these slides, but I've been able to provide this library for assembly, C, and even basic. The basic version uses some machine code above memtop that you access with GoSubs. As mentioned at the start, these then remember their colour and look after themselves. So unlike a matrix of traditional LEDs, where you have to keep scanning the rows and columns, once you've updated this display, your program loop is free to get on with its day until you next want to update the display. And that's all there is to it.